Okay, welcome back. For the last couple of classes, we've been talking about projectile motion, and so far we've covered horizontal. And what you need to remember with horizontal launch problems is that the initial vertical velocity, v1y, is 0. Okay, that's what you need to remember there. That's the most important thing. When you're doing the next case, the angled launch upwards, in other words, it's launched at a certain angle above the horizontal, what you need to remember there is you need to break that launch velocity down into a horizontal and vertical component. And remember that the initial vertical velocity, if it's launched at an angle above the horizontal, is always positive. Okay, what we're going to do this time is we're going to take a look at the third possibility, which is the trickiest one, and it's trickiest because the angled launch down, you'd handle it almost identical to the way you do the angled launch up. In other words, you have to break the velocity down into components. But you have to be careful because if it's launched downwards at an angle, in other words, an angle below the horizontal, the initial vertical velocity is down, so which means you make it a negative number. That's the thing that's easy to forget. So when you're doing these downward launch problems, that's the most common mistake that students make. So be really careful with that. So just to recap, when you're doing an angled launch, okay, remember that v1y is not 0 anymore. That's only if the launch is horizontal, only. Okay, angled launch, you have to use the launch angle to find your components for the initial velocity. And Vx is v cosine theta, Vy is v sine theta. And that's the initial velocity vertically. Okay, and of course the vertical acceleration is still gravity, negative 9.80 meters per second squared. But the most important thing to remember here, okay, I'll draw a box around it. v1y will be a negative number. Remember that. Like I said, it is the most common mistake that's made in these types of questions. So what we're going to do now is we're going to look at some more examples again. And we're going to look at examples from old public exams. Now what you're going to find on the public when it comes to downward launches, downward angled launches, is there's very few multiple choice. In fact, going over the past few years, there's actually none, not in the multiple choice, there's none there that specifically deal with angled launches downwards. So we're going to look at some general multiple choice again for projectile motion, some things on vectors and things like that. And then we're going to look at a couple of long answer questions from old public exams that do deal with angled launch downwards. Okay? So let's move on and take a look at some general projectile motion multiple choice questions. Okay, so in the first one there at the top of the page, top of your screen, you see a ball thrown in the air and it traces the path shown. In other words, it follows a parabolic path. And you can see the path there. It starts here, comes up like this, reaches the top, and then starts to come back down again. So it's moving horizontally because it's going from left to right, but it's also moving vertically. It's going up and then down. So which one of the statements then is true? Let's read them one at a time. The acceleration of the ball at the top of its motion is 0. Well, that's never true because the acceleration in these types of problems, the acceleration is always the same. It's always negative 9.80 meters per second squared. And it doesn't matter where the ball is in its path, that acceleration doesn't change because gravity doesn't change. Gravity is the same everywhere. So that one is not true. The acceleration is never 0, not the vertical acceleration anyway. The acceleration of the ball keeps changing? No, that's not true either because we just said that it's always negative 9.80 meters per second squared. So we can rule that one out. Can we say the velocity of the ball at the top of its motion is 0? Well, that one's a little bit tricky The vertical velocity of the ball at the top is 0, but it's still moving horizontally, so that's tricky. So Vy is 0, but Vx is not 0. So we can rule this one out too. The velocity is not 0 at the top because it's still moving horizontally. So by process of elimination, it's got to be the last one there, D. It has to be. There's nothing else left. And that one is true anyway, isn't it? The velocity of the ball keeps changing. We know that. As it goes up, it slows down. When it reaches the top of the path, it's only moving horizontally. Then it starts to speed up vertically again as we go down. So the velocity vector is always changing. It's always changing. Okay, the second one on the page there, the one on the bottom, that one is what we call a level 3 question. That one's a level 3. That one requires a bit more understanding. We've got two arrows launched at the same time with the same initial velocity. The only difference is the launch angle is different. The first one is launched at an angle of 60 degrees to the horizontal. So arrow X goes up like that at a 60-degree angle. That's arrow X. Arrow Y is launched at a 45-degree angle like that. Okay, this is 45, and that's arrow Y. Now, we want to know two things. Okay, there's two things mentioned in the choices there. The flight time is mentioned, the time in the air, and the range is mentioned. Well, the flight time depends on one thing and one thing only. It depends on the vertical velocity at the beginning, okay, and the height. Okay, but if we're talking about going over level ground, then the height's not going to matter, because the height at the beginning and the height at the end are still the same. So the flight time is just going to depend on which one would have the largest initial velocity in the vertical direction. Well, remember this, that V1y equals V sine theta. Now, if you think about the sine function, as the value of the angle gets larger, so does sine. And if you're not sure, if you don't believe that, just try it on your calculator. Punch in sine of 60 and sine of 45 and see which one is the bigger answer. And you'll find that sine of 60 is larger than the sine of 45. So that means that arrow X has a larger initial vertical velocity. Therefore, arrow X is going to be in the air for a longer amount of time. So right away, we know it's got to be either A or B. We can rule out these two. Arrow X is not going to be in the air for a shorter amount of time because it was shot more straight up in the air. So that's going to make it stay in the air longer. However, what about the range? Well, the range, remember, depends on two things. The range depends on the time. Well, we already said the time for arrow X was a bit longer. But it also depends on the horizontal velocity. Now, the horizontal velocity is calculated using cosine. And the thing about cosine is, as the angle gets bigger, cosine gets smaller. So although arrow X has a larger vertical velocity, at the same time it has a smaller horizontal velocity. Okay, so even though it has a longer time, it has a smaller horizontal velocity. And when you work it out, you'll find that arrow X wouldn't go as far as arrow Y. Now, there's no numbers given here to work with, so that's what makes it a little bit more difficult. But let me give you a little tip. If you want to get the maximum distance out of a projectile, the optimum angle is 45 degrees. So 45 degrees gives you one of the longest ranges you can get. Okay, and if you don't believe me, just try the few numbers. Try, for example, just work this out by saying that the initial velocity was 100 meters per second. and get your different values for Vx and Vy. See how long it stays in the air. See how far it travels. And you will find that arrow X is in the air for a longer amount of time, but it doesn't go as far. So B would be the correct answer there. Now, that, like I said, that's a fairly difficult question. That's a fairly difficult question. Let's move on. Let's try another multiple choice. And again, like I said, these are general multiple choice that are not really dealing with downward launches because it's very difficult to find multiple choice on those. They're generally kept for the long answer part. But let's take a look at this next question. We got a football that's kicked and follows a parabolic path. So in other words, the path of the football looks like this. Goes up in the air, follows this curved shape, okay, and eventually it comes right back down to the ground again like that. Okay, we want to know the velocity of the football at its maximum height. Well, what you got to remember is the velocity has two parts to it. It has a horizontal and a vertical part. But remember, at the maximum height, which is right up here, that football is not moving up or down. It's already at its maximum height. It's just finished moving up. It's about to start moving down. So right now, at that point, it's only moving horizontally like that. So that means that there is only one answer. That's the possible answer right there. It's A. It has to be. Because at the maximum height, it's only moving horizontally. It's not moving vertically. So all we get is that horizontal line there, that horizontal vector. And the last question there on that page, that one, if you think about it, is fairly easy. Okay? And that one should be a level 1 question. In other words, you should be able to read that, boom, I know the answer. There's no calculation necessary, it's just something you're supposed to know. You want to know the direction of the acceleration for any projectile. Well, remember, the only thing that's making a projectile accelerate is gravity. And gravity always points in the same direction, down. So because it's the acceleration due to gravity that's causing the acceleration of the projectile, then the acceleration for any projectile will always point down. Always. No exceptions. All right, let's try a couple of long answer questions. So for this one, we've got a ball that's thrown from the top of a roof of a building or the top of a cliff or something like that. But the point is, it's thrown at an angle below the horizontal. Below the horizontal. And we want to calculate the range of that ball. So in other words, we want to find dx. Now, before we can find dx, we're going to need to know vx, and we can find that from the information we're given there very easily, because that's just a component of the velocity that we're given. And we also need to know the time. We're going to get the time from the vertical. Just watch. So, first step is whenever you have a velocity at an angle like that, you should always find the components. Okay? Find the components first. So when you do that, here's what you get. You get, okay, here is the y component right here. Okay, so in this particular solution, and I took this solution actually from the answer key for the publics, in this particular solution, they actually did this right in the calculation. 82 times the sine of 53, okay, is the component of that. And what you got to be careful with is that's actually going to be a negative. Okay, but in this case, because you're squaring it, the negative is going to disappear anyway. So what they've done here in this solution is they've decided to find V2 first. They've decided to find V2 first. Now there is another way to do it. Let me just very quickly jot down another way you could do that. You could have said dy equals V1y times t plus a half of ay t squared. Now if you had done it that way and plugged in dy as negative 10, v1y as 82 times the sine of 53, and ay as negative 9.80, you would have ended up with a t term and a t squared term. You would have had to use the quadratic formula. Okay? And we did examples of that back in the topic 1 class, back in class 1. So if you want to go back and see how that's done, you can check that out there. I prefer this method, the method that they've used right here. I prefer to find v2 first. That's a little bit easier. It's a little bit easier because it's very easy to make an error when you're using the quadratic formula. You got to be really, really careful. There's so many numbers, so many signs to get right. It's a lot easier to do it this way and get the right answer. And when you do this, you notice the answer is a negative 67. Now, how do you know it's negative? Because when you take the square root, there's actually two square roots, right? There's a positive one, which we call the principal square root, but there's also a negative one, because when we square a negative number, we still get a positive answer, okay? So that's why I put a negative sign there, because I know that when this ball hits the ground, the instant before it hits, it's got to be traveling down. It can't be moving up or it wouldn't hit the ground. It has to be moving down just before it hits the ground. That's why we make that a negative. So in this particular solution, that was worth 1 mark for doing that. And then you use that using the acceleration formula to find the time. Now, here's the key to this. V2 we know because we just found it, negative 67.0. But take away V1, take a look right here. Notice this negative sign here? That's because when you find the component, the vertical component of that initial velocity, it's negative. And you know it's negative because if you look at this, this ball was thrown downwards initially. That's why we have to make that velocity negative. Okay, you work that out and you will get a time of 0.153 seconds. Okay, that's the time. Once you know the time, then you do this. dx equals vx times t. Now they said tx there, but that's the same thing. It's the time we just found. There's really only one time. The tx and the ty, same number. Okay, so dx equals 82 times the cosine of 53. That is the horizontal component of the velocity, multiplied by the time, and that gives you an answer of 7.55 meters. Now, you'll notice that on this particular exam, when you get down to the last step, there's an extra mark for science and communication skills. Now, like I mentioned before, what that means is that mark is split into 2 parts. There's a half a mark for significant digits, having the correct number of significant digits. There's another half mark for having the correct units. If one of those is wrong, you're going to lose the half mark. In other words, you would not get full marks for that particular question without having the right number of significant digits and the right units. But on the other side of the coin, even if you just wrote down an answer without showing any calculations whatsoever, if you just wrote down an answer, and believe me, I know this because I have marked the public exam before, and this is the way it works. If you just wrote down a number with the correct number of significant digits and the correct units, you would get that 1 mark for science and communication skills, believe it or not. Okay, you would get that mark. Even though you didn't show any workings, your answer might be wrong, but as long as it has the right number of significant digits and the right units, you would get that mark, because that's one of the things being evaluated in this question, that you know how to write down the correct number of significant digits. So you knew by looking at this question that the answer should have 3 significant digits because that was the least number given. And you also knew that the range is measured in meters, so you knew what the units would be. So you would get that 1 mark just for writing down a number, even showing nothing else whatsoever. Now, I don't recommend you do that, but if you have no idea how to do it, then at least write down a number with what you think is the correct number of significant digits and the correct units, and you could get that 1 mark. Okay? Tip for today. All right. So that's that one. Let's try another one that's similar to that. Now this one's a little bit different. Okay, this one we've got two balls, ball A and ball B. Now ball A rolls down a ramp, so does ball B. The difference is ball A gets to the bottom of the ramp and starts to roll across the table. So ball A leaves the table horizontally. So that's actually a horizontal launch. Whereas ball B leaves the edge of the ramp at the edge of the table, and it actually has an initial velocity downwards at an angle. And it's obviously an angle of 30 degrees because that's what's there in the on the ramp. So ball A, we're going to find out now what the range of ball A was, because the question here asks us which ball would travel the greatest horizontal distance from the base of the table. In other words, which one has the biggest value of dx. So obviously you're going to have to do both of them separately. So let's try that. So here's the first one. First thing we're going to do is for the vertical, and remember, because this is a horizontal launch, we don't need to worry about components of the vector, do we? Even though it rolled down a ramp up here, when it left the table and started acting as a projectile, because it doesn't become a projectile until it leaves the edge of the table and it starts to fall due to gravity. Okay, so when it left the edge of that table, it was a horizontal launch, so no components to worry about. So what we do is, you get a half mark for doing this, saying that d equals vt, v1t plus a half at squared. You would get that because remember, v1y is 0. It's a negative 1 meters because it ends up 1 meter lower than it started up here. And the acceleration obviously is negative 9.8. So we do that, we get this, and that would give us a value of, once we took the square root and everything, 0.45 seconds. That's the time. That's how long that ball remains in the air as it's falling. So obviously that's how long it's traveling horizontally as well. And of course, the horizontal velocity was given. And all we got to do is say d equals v times t. That's it. d equals v times t. Uniform motion, remember, for the horizontal part, it's always uniform motion, no acceleration. So d equals v times t, 2 times the time that we just found, 0.45, and that gives us a range, a dx, of 0.90 meters. That's 0.90 meters. That's ball A. Now we know how far ball A went. Now we got to figure out how far ball B is going to go. And if you were to think about this and use a little bit of reasoning, maybe a little bit of common sense, you would probably figure out that since ball B is thrown downwards, it's going to hit the ground faster, and therefore it's not going to go as far, right? So we could probably figure that out using common sense. But you do have to show this. It does say calculate which ball. So you do have to show calculations. So let's do the same thing now for ball B. Now for ball B, though, you got to be careful because remember you have to find components for this one. Okay, so let's do that. So the components, remember now, the V1 is going to be a negative 2.0 times the sine of 30. But it's all squared. Okay, and remember, when you square it, that negative sign is not going to matter. But the reason that negative sign is there in the first place is because it's a downwards launch. Anytime you have a downwards launch, it's always negative. So for this one, the person who did up the solutions for this opted to use that same method again. Like I said, in my opinion, that's the better method to use because it's easier to get it right. Okay, unless you're really comfortable using the quadratic formula and you're really confident about it, I would recommend you stay away from it. Because you can always do it this way. You can always find V2 first. So you plug in everything you know, okay, and that will give you this answer. V2 equals a negative 4.5. So when the ball reaches the ground, this is in the vertical direction now, so this is the y's, V2y is negative 4.5. And again, when you take the square root of a positive number on your calculator, the square root is always going to be positive. But remember that there's also a negative square root that your calculator doesn't show you. And in this case, because the ball is moving downwards when it strikes the ground, it's the negative one that you're looking for. Okay, so we know that v2y is that. Now we do this. We use the equation for acceleration, v2 equals v1 plus at, and again, this is in the vertical direction still. So we plug in the numbers that we know, and remember that v1y has to be negative. Okay, don't forget to put that in there. That's so important. So important. And we get a time of 0.36. So it is a lower time than we had the last time. It does get to the ground sooner, which makes sense because the ball is thrown towards the ground. So it's already moving downwards at the beginning. So when we do that, now we have to find, this time we do have defined components, right? We do have defined Vx. And Vx, remember, is 2 times the cosine of 30. Okay, because that's how you always find it. This one we don't have to worry about a negative sign because the ball is rolling to the right, horizontally. Okay. Multiply that by the time, and you get this distance, that range. There's dx. Now remember, for the last one, it was actually 0.90. This time, it's only 0.62. So the prediction is correct. Ball A does travel farther. The one that rolled off the table horizontally will go farther. Now, if it went up in the air, if it was of angled launch upwards, it probably would have went even further again. Okay, but that's not what the question asked. Okay, so there's a couple of examples of angled launches downwards. And like I said, the key thing to remember, most important thing, is that negative sign on your initial vertical velocity, on your v1y. Now, if you'd rather do these separately first, if you'd rather say v1y equals v sine theta and plug the numbers in, that's fine. And then put that number in this equation, that's quite all right. That's the way most people do it. This is just a quicker or shorter way to do it, that's all. That's the only difference. You can do it either way you like. All right, so that concludes projectile motion. That concludes projectile motion. What we're going to be doing in the next class is we're going to take a look at Newton's laws. So we're going to take a look at forces and things, but primarily what happens when you put objects on inclines, inclined planes. How does that change things like the free body diagrams and stuff like that? Okay, so we'll deal with that in our next class, which will be available next week. So good luck with your studying, and we'll speak to you again soon.